Okay, good morning, everybody. I'm Julien Lesgourg. So I would like to thank David Spergel and the Simons Foundation for the opportunity to give a talk in this amazing place. And thank you for coming. I will hope that it will be a useful and fun meeting for you, and fun not only because of my French accent. I hope it will be useful for your work. And I think this depends also if you are very interactive or not. So because you were so many registrants, the people at CCA kindly agreed that we would move to this auditorium, which is very nice, but maybe it's a bit more solemn, while in a smaller room, you would be more in hacking mode. But please stay in hacking mode. Please use your laptop. Please do little experiments with the code while I'm talking. And please do not hesitate to interrupt, okay? So the workshop is broadcasted in real time on Zoom. I think there are a few people connected. If you are following on Zoom, please stay muted. But if you have a question, you can unmute and ask your question. Okay, very good. We are all set. So you have seen the timetable. We are going to start with the most basic things. We have a series of courses on class. Okay, most of the workshop is on class, and things then will be presented by me. But there will be a very interesting part devoted to the developments for second-order perturbation theory, which are implemented in the code Song. So Song will be presented by Christian Fiedler, who is sitting here, and Song is a small time of the duration of the workshop, but in terms of amount of work and equations, it's a lot more than class, actually. So that's a bit unfair. But okay, so the plan for class is the following. There will be a series of lectures on the very basics of the code, the underlying theory, what is the physics implemented in class, how do you use it when you are really a beginner from the terminal, or when you do more sophisticated things from a notebook, Python notebook. We will explore a little bit all the possibilities of what you can do with this Python notebook and with the code. And then tomorrow we will go to the more hacking level, and I will tell you some essential things you should know if you want to modify class. So tomorrow will be more about really the details of the coding style and how do you deal with error management and how do you introduce a new physical ingredients. And at the end of tomorrow, there will be a lecture where I will announce what are the ongoing and developments and future plans for the releases over the next year. So we will have 2 exercise sessions also, and if you want to benefit from the exercise session, really it's nice to have the code already installed and working before. This is why we circulated an email on Friday. If a few of you still have problem installing a class, I understand that on a Mac it can be sometimes a bit problematic to have class working with its Python wrapper because of the dialogue between C and Python on a Mac is not always blue sky. So don't hesitate to let us know, and we can help you during the pauses such that you are fully ready and set for the first exercise session. Very good. Let's start with the basics then. So class is of course not the first public Einstein-Boltzmann code. Let's start from a short historical review. So all this business started when Bertschinger in 95 and Cheng-Pei Ma and also somebody else who was helping implemented the most important equations for CMB physics in a package in Fortran called Cosmic. And this was really a brute force approach. It was very heavy. It was taking hours. There was a big breakthrough very soon after, just one year after, when Seljak and Zaldaryaga came up with a line-of-sight method. You probably know what it is. If you don't, I will have a slide on this in the theory lecture. So the CMB fast then became much faster. CMB fast was still based on Cosmics. Actually, the first version of CMB fast was Cosmics with, on top of it, a few new functions that were enough to completely boost the code. So this was released in '96. At the time, I was a first-year PhD student. And I remember everybody got very excited. I myself started to hack CMB fast, I think 3 days after the release. So I've really followed all this history of Einstein-Boltzmann solvers. Then Uros and Matthias implemented a lot of new physics in CMB fast. They implemented the calculation of polarization E and B mode. In cosmics, there was some polarization, but E and B mode had not been clearly defined at that time. So they added E and B modes. They added equations to deal with the case of an open universe, because negative curvature was popular in these years. And they added the first version of CMB lensing with a flat sky approximation. So the thing is that Uros and Matthias were really interested in adding new physics, but not so much in organizing and maintaining the code. So CMB fast became kind of a bit messy. There was some need to clean it up. And this was done by Anthony Lewis and Anthony Chalinor. Anthony Lazenby was also taking part in '99 with the release of COMB. So COMB was still partially based on CMB fast. It was taking some bricks, some blocks from CMB fast, and it was arranging them differently and using the features of Fortran 90. So it was not completely independent. It was mainly a restructuring of CMB fast. And also, progressively, Anthony Lewis added a lot of new physics in COMB. He had the first version of calculation with positive curvature. Together with Anthony Chalinor, they defined a better version of CMB lensing, which is a full sky version. They did lots of clever algorithms, new physical approximations to speed up the code, so it became really more efficient. They did new species, new observables. As you know, COMB has been developed a lot. It's a very big code, and it's still very actively maintained and very actively used. Then there were other attempts. Some never became public. Martin White had his version. Some folks in Paris had another version. They didn't make it to the public release. There was a public release of a nice attempt to write CMB code in object-oriented style in C++. It was called CMB Easy. It was done by Michael Doran, a German student. It was a nice code. It was also improving on several fronts, like the tight coupling approximation or the possibility to choose your gauge. But Doran left physics and did not push the code far enough in terms of precision. So CMB-Easy is still available, but not maintained. If you would try to fit Planck data with CMB-Easy, you would get some bias on the final parameters. So then we came with class in 2011. I will give you what were our real motivation in the next slides. So this was done in an effort together with Thomas Tram. At that time, he was a PhD student visiting CERN, where I was working. He helped me a lot to complete the last stage of the writing of class. And it was not just a rewriting. We came also with new physics, new features, and these are things I will present in the next lecture. So you will see that we have different equations for polarization. We have some new numerical approaches, new physical approximation. We have more species and physical parameters than COMB. We have also different observables. So the codes are not really fulfilling the same tasks. So we will see there are more codes, maybe one or two more to come. I don't know, I'm not sure. Sometimes I hear rumors, but then they are not confirmed. But anyway, both COMB and class are both actively maintained. So if you want to fit data with high accuracy requirements, nowadays you have to choose between these two codes. Okay, so what was the motivation for developing this code class? Well, it started like a request of some people at a high level in the Planck collaboration. because people realized that they were spending a lot of money and effort to measure the CMB with high precision, and it would be analyzed with one code, with a risk that if the code has a systematics in it, then all the result of this expensive experiment will be some biased cosmological parameters. So they wanted an independent code. And they wanted something written from scratch and not just by copy pasting equations and reshuffling them, which had been the case more or less between the last version of CMB-Fast and the first version of COMP. So this is what motivated me. At the beginning, I worked alone for a few years, and then I finished with Thomas in 2011. And indeed, one of the first tasks was to compare class and COM in the highest accuracy limit. This is a comparison that you find in one of the papers from 2011 called Class 3. And this comparison was really interesting because it revealed at the beginning, it revealed some inaccuracies in the two codes. So the high precision limit of the two codes were still a bit too far from each other. Not very far, but too far for claiming that we can predict the CMB spectrum at a much better precision level than the Planck error, for instance. So I really worked hard to understand what was the difference. When it was a problem with class, I improved it. When it was a problem with COM, I wrote to Anthony, who took it into account. And after this process, we managed to have a high accuracy limit of the two codes matching each other at the 10 to the minus 4 level, so 0.01%. And since the codes have been really developed independently, I think it's reasonable to say that given our way to model lambda CDM, we don't have numerical errors bigger than this level, at least if we are ready to run the codes in high precision mode. And so we have some reference to compare with. And now when we put a new ingredient and we are trying to tune the precision parameters, we can compare to a reference version, which is one of the two codes in this high accuracy limit. And we know that we have set parameters in order to match a targeted accuracy of 0.2%, for instance. So this was really the main motivation, but then the class project went beyond this because some people, including myself, were excited to develop it and a new feature and do real research with it. So these are the goals of class. It looks like commercial so far. In fact, I just tell you what we tried to achieve, and then it's of course the user who decides if it's achieved successfully or not. So the goal of class was to be as general as possible with a lot of cosmologies implemented, lots of species, adding a lot of new physics, but not at the expense of performance. We wanted to be modern, which means a clearly structured code, very modular, with independent module, independent tasks, no overlap between them, flexible and wrappable. So you can call class from the Python wrapper or the C++ wrapper. There are some Python extensions which are just codes to achieve some automatic precision test of class that you can run with each new version to check that you are not losing accuracy. Okay, the code is meant to be user-friendly. I think this was never a big worry for some of our competitors and friends. So it's very much documented inside the code. There are lots of comments in the code. There are also some documentations online. You will tell me if you like them or not. It's always possible to improve a lot on this side. So we really try to make the code easy to follow, to analyze, to understand. I will show you concretely how we try to do this, what we did in order to achieve this. Because our idea is that we want this code to be easy to modify by people in the community of theoretical cosmology. And actually, when you look at who is using which code, you realize that very often people closer to astrophysics don't need to put more cosmology in a code. They need to use this Boltzmann code almost as a black box to get their prediction for lambda CDM and then manipulate the output, convolve with redshift bin, selection function, etc. And in this community, COMB is still very highly popular. And then you have the community of theoretical cosmology, where people want to implement new feature. I don't know, a new dark matter species, a new approximation, a new model of modified gravity, whatever, or just a new observable also. And then when people arrive to the stage of modifying the code, it seems that class becomes very popular and very much used in this case. Okay, and of course we wanted to have a code which would be accurate and fast as its competitors. So the speed is roughly the same as COMP. It's the same order of magnitude. And which one is the fastest at the moment depends a lot on what you are doing with it. If you are going to put massive neutrinos, for instance, then maybe class is going to win. If you don't, depending on what you are doing, well, the codes are roughly comparable. But at the end, I will give you some plans that we have and that we started already to implement, where we are talking of speeding up class by at least an order of magnitude. We have ideas for that, and it's in the process of being done. So this will be for tomorrow afternoon. Okay. Next is a motivation part. So what can you do with a code like class? Well, of course, you can do a new fit to the data with a new model. So you can do your research with it. But the code is also meant to be used for explaining physical effects in your paper or in your seminar. Produce a nice plot for your next seminar where some effect is enhanced, or also use the code for teaching or outreach. So you can use it in many ways. This would be the most classical one for a CMB physicist, to output the different components of a CMB spectrum. You could also, for the purpose of understanding better the physics or explaining it, you could decide to break your CMB temperature spectrum in individual effects. So for instance, to see the effect of adding or removing lensing, that's the difference between black and red, or decompose the CLs by asking in your input file to break into a Sachs-Wolf, early integrated Sachs-Wolf, late integrated Sachs-Wolf Doppler effects. There is also a polarization component which is too small to be seen. If you are more a large-scale structure cosmologist, you can, of course, output the matter power spectrum, the linear one, because it's a primordial goal of such kind of a code, or maybe some corrections coming from HaloFit or HM code or an algorithm like this. Okay, this is all very basic. Now, less basic things. If you want to understand what is a new effect in your new model and to explain it, for instance, to students or in a seminar, then maybe you want to do some more original plots. Maybe you want to choose a wave number and show the evolution of the different perturbations as a function of the conformal time. So this is a plot showing the evolution of the most interesting quantity for CMB physics that I use when I teach CMB physics to master students. Or this is the opposite here. You fixed a time or a redshift, and at this time or redshift, you try to plot different perturbations as a function of wave number. Of course, it's very nice to do this if you want to understand how things evolve with respect to time. So all this can be done without hacking the code. You don't need to open it and to write a print, blah, blah, blah. From the input file or script, you have full control on this kind of output. Now, if you are a large-scale structure expert, maybe you don't care so much about the matter power spectrum. You want to compute the CLs of lensing or the CLs of number count or galaxy density corrected by redshift space distortion, etc. So all this is also implemented in the code. Also, the cross-correlation between the two is implemented with lots of parameters to tune the redshift bin of your selection function, or do you want to include the redshift space distortion or the lensing of the number count of galaxies. All these things are coded in. Okay, and then maybe again for doing a nice plot in your paper of what is the role of, I don't know, your new dark energy model. Maybe you just want to show the evolution of background densities with time, or some angular diameter compared to luminosity distance. So all these background quantities can be plotted, again, without hacking the code, but just asking this kind of plot at the level of the output file, and the same for the thermal history. If you want to, for your seminar, to explain the evolution of the hydrogen or the global ionization fraction in the universe as a function of redshift, or the visibility function that is very important for the CMB, you can do it. Okay, this I already done. What else? Yeah, so there are many other quantities. For instance, you can try to compute the pyramidal spectrum in a complicated model of inflation with some inflaton spectrum. For this model, you can ask the code to compute numerically for you the spectrum of scalar and tensor perturbations, and then you can plot them. And okay, all the rest are things that I essentially already mentioned. Okay, now you can play with the output inside the script. That's very nice. For class, it's possible since there is a Python wrapper for class. Now COM also has a Python wrapper, so you could also do it with COM. And this allows you to work in a much more modern way, in which you are not going just to run the code 10 times from the terminal and then assemble everything in a figure. But you run the code from a Python script, and directly inside this Python script, you do some nice manipulation of the outputs of your data in order to make some nice plots. So for instance, we will comment on a script that you could use to check the effect of a given cosmological parameter on any observable, like the CLTT of the CMB or the PK. So once you have this script, okay, you want to explain what is the effect of adding extra relativistic species in cosmology for the CMB and the matter power spectrum. With this script, in 2 minutes, you get this kind of nice plots. So the exercise session will train you on doing this also. You can do more advanced stuff. For instance, this is a script that is publicly available. When you download class, you have examples of scripts. This is one of the most sophisticated that you have when you download class. The colors show the amplitude of some perturbations, more precisely transfer functions, for the photon density and for the metric fluctuation phi as a function of conformal time going from the early universe to today, and wave number coming from large wavelengths to small wavelengths. And with this kind of colors, you can really appreciate the evolution of these perturbations. And you can then use this for your cosmology course. You can see very well that quantities are frozen on super-Hubble scale, and you see the acoustic oscillation on sub-Hubble scale during radiation domination, which tend to be damped during the beginning of matter domination. Here you see really everything. And the same for phi. You can, with these plots, you can really explain what is the early integrated Sachs-Wolf effect, which comes from here, or the late one, which comes from here. Okay, so this is to advertise the advantage of using these Python scripts. Okay, so you can do all this for a wide range of cosmological models. I really think that any cosmology implemented in COM is in class, and I think we have a few more things. Okay, so for instance, for primordial perturbations, we have more options for dealing with isocurvature modes with arbitrary correlations. This is becoming less and less fashionable because Planck has found no evidence for isocurvature modes. We have lots of options for playing with a complicated input spectrum with a feature, or for computing numerically the primordial spectrum by integrating quantities during inflation. In the neutrino sector, we have, because neutrino cosmology is one of my favorite topics, we have implemented a lot of freedom. You can play with lots of things if you like this, with a neutrino chemical potential, with arbitrary modification to their phase space distribution, You can modify the phase space distribution up to the point where we are not dealing with neutrinos but warm dark matter, so a lot of flexibility with warm dark matter. You can implement the role of the mixing angles between neutrinos if you do very high precision stuff. For dark matter, so we have the cold, the warm dark matter, but we also have the annihilating dark matter, the decaying dark matter, and interacting dark matter is implemented in non-public version, but they will be public soon, as I will say tomorrow. For dark energy, the first feature is like in COM. You can play with a flexible equation of state for the pressure to density ratio of dark energy, and with the sound speed of the dark energy perturbations. You can also directly integrate the equations of quintessence. So it means you can have quintessence not treated as a fluid, but really as a scalar field with a Klein-Gordon equation and perturbation to the field. So the code is able to directly evolve quintessence for a variety of quintessence potentials. If you are a fan of modified gravity, then probably you want to switch to the high class branch. So this is not part of the public class, but it's a branch that has been developed by Bellini, Savicki, and Zumalakaregui. I have just a little bit, just very little, but so this branch is like an official one. It's fully approved in a sense, and it's updated usually when class is also updated, and it contains lots of parametrization of modified gravity model. There are all these Horndeski models, but there are different limits of the Horndeski model which match exactly what is implemented in EFT-COM or MG-COM. Okay, another feature of class, which I think is really different from COM, is that it's multi-gauge. So by default, you get it with a synchronous and Newtonian version of the perturbation equations. And everything is coded in such a way that if you want to add your third or fourth favorite gauge, it's very easy. And I think we are going to, okay, many people are using the Poisson gauge or the N-body gauge. We decided that we would release one of them soon because the modification already exists. Then there is this extension to second order perturbation theory. Extension is really minimization of it because it's a huge extension. And this is a code song that Christian has developed with Guido Pettinari and Thomas Tram, and that he will explain this afternoon and tomorrow. And there are other branches of class which are specialized in different things. This exo class is specialized in exotic energy injection mechanisms. There is a version called class SZ of Boris Boliet, which is specialized in predicting Sonayev-Zeldovich observables. Exo class is from Patrick Stucker and Vivian Poulin. So progressively, we tend, when there is a branch like this, which is very well tested and efficient, we tend to merge these branches with the main class. For instance, there was a branch at some point called class GAL. Class GAL was specialized in computing the number density count CLs in presence of GR corrections. But class GAL has been entirely absorbed by the main class. This is why I don't advertise it here. Okay, this is a funny application. There is also, when you download the code, you have a directory called the Real Space Graphic Interface, and it allows you to show nice little movies to your friends or your students when you will become more seniors or your colleagues. So it's really a graphical visualization tool based on class. And Christian is going to do a little demo for you such that I can rest a little bit. And then I will go on with a lecture. Okay. I'm not sure if I have. Yeah, you can take this one, or you need to unmute it. Here, yes.
Yes? It works. No, it's fine. I'm just taking a few minutes. All right, so this is the real space interface where you can see the perturbations evolving in real space live. And one can start here by setting initial conditions. And this is our random realization that we have drawn here for the photon density. And you can modify all kind of cosmological parameters here. And then let us now keep them at the standard values and run the simulation. So this will take a little bit of time to compute all of the Fourier modes. And then using the transfer functions that class computes and the random initialization that we have drawn here completely randomly, we can now let these perturbations evolve in time. So let's play it on infinite loop for the photons first. Okay. So this is how the perturbations now evolve in real space. And what you can see here is initially, the modes are kind of constant, and they enter horizon. Now you see acoustic oscillations and silk damping erasing the small modes. And then after decoupling, you have the free streaming for the photons, so the perturbations just stream away. And then, of course, we can not only look at the photon density, we can, for example, look at the neutrinos, where you have a very different picture, because neutrinos initially start with similar initial conditions, but because they are not coupled to the baryons, they immediately stream away. So you see that all of the small scales get erased very quickly. Then we can look at cold dark matter, for example. And for cold dark matter, you see that initially the photon perturbations are imprinted in the cold dark matter by gravity, and then it kind of freezes and stays constant. And this is simply because we have scale-independent growth, and the code simply normalizes the output to one reference scale. So in fact, these perturbations, as time progresses here, they are continuously growing, but to keep the output constant, this is completely absorbed. And then finally, we have the baryons, which you can see here. So initially, the baryons, of course, are tightly coupled to the photons, so it looks exactly like the photons. But then they decouple from the photons, and then the cold dark matter perturbations are gravitationally imprinted into the baryon fluid. Okay, so this is what you can do with the code to really show nice visualizations of the class output, not in Fourier space where we are used to understand things, but in real space. You can do also more with this one. So let's stop this here. Let's go back to the initial time. And we can, of course, get new initial conditions. They are always randomly drawn. But what we can also do here is look at Gaussian initial conditions and start with a little peak, single peak. Now I will run simulation again for this little Gaussian peak, and then we can observe how this peak will evolve. Okay, well, let's start again with the photons, and let's run the simulation here. So what you see here is, of course, the photons are tightly coupled to the baryons, and because of the photon pressure, there's a shell that is ejected from the central peak. And then later you see that this shell suddenly starts to disperse, and this is exactly when the photon free streaming starts now, where this ejected shell starts to disperse. Then we can look at the baryons, which look very similarly, because initially they are tightly coupled to the photons, but then at some point they just start to freeze out. They are not dispersed like the photons. And then, for example, what is very interesting is to see the neutrinos, where you have a very different ejection. You don't have really a massive shell that has a momentum that is being ejected, but you just have the pressure diffusing this Gaussian term. And finally, let's look at the cold dark matter, where because of the rescaling, not too much is happening. So the cold dark matter essentially just stays where it is. There's a little bit of gravitational interaction with the photons initially, and then the perturbations just grow. Okay. Yeah?
Is there any way to have a color bar so we actually know the amplitude?
Yeah, this is not currently not possible, but of course this is something that we want to do, because right now it's a bit disappointing to look at the cold dark matter because nothing happens for the cold dark matter. But of course what happens is that you have the completely scale-independent growth. So as time progresses, the peak will just become larger and larger and larger. And then of course if you had non-Gaussianity in the code, you would see that the peak shrinks as soon as nonlinear effects become relevant. But because this is, of course, completely linear, the structure that you have in cold dark matter is frozen and just grows in amplitude.
Yeah, we will improve it. This comes from 2 projects from 2 bachelor students of 3 months each. So they have done some good job. It's not us, actually. And there is a lot of margin for going even beyond. Yeah. All right. Do you have questions at this point? No? So I think we are done with the general motivations, and we can go into a little bit more detail. So what I want to talk about now is the class coding spirit. And these are a list of tasks assigned to ourselves for developing a code matching matching these features that we want of a code being user-friendly and efficient, etc. So it's still a bit general, and we will go into concrete details progressively. So how do you get a code to be understandable? So our choice was to follow literally the notation of one of the most paper in the literature, which is one of my Bibles. It's a paper of Mayen Bertschinger from '96. I guess you all know it. It presents the CMB equation in a very nice way, and also matter power spectrum equation. We follow exactly this notation, this convention, with the same names. So of course it's C and not LaTeX, so the name are a little bit more cumbersome, but you could almost write a script that would read our C code and convert it to LaTeX, and you would immediately find the Mayen Bertschinger equation. And like them, we coded everything in Newtonian and synchronous gauge. Okay, then one thing we tried to achieve was to have a flexible input. So the input parameter you pass goes through a layer of logic. This layer of logic knows a little bit of cosmology and tries to make sense of these parameters in a slightly elaborated way. So this is not like in some codes where you just have to switch between entering the big omegas or the small omegas. Here there is a lot more logic. And taking an example, if you want to fix your Hubble rate, you can pass a big H0 or a small h, or you can pass 100 theta s, which is another way to fix s through the angle under which you see the sound horizon on the CMB. So in an example like this, the code knows that you should pass one of the three. If you pass two of these parameters or three of these parameters, it will complain and stop. If you pass none, it will always use a default value, which is always the simplest thing. So the simplest thing is to compute lambda CDM with Planck parameters. If you don't give any input parameters to class, it will do this, lambda CDM with Planck best fit. Okay, and so when you run the code, this is just one example, the code will check which one you entered, and from this one, it will infer the others and give it in output in case you are interested. And the same with lots of other things. For the density of photons, you can put the temperature of the CMB or big omega gamma or small omega gamma. With the neutrinos you will see are called non-cold dark matter. You can put a big omega, a small omega, a mass in electron volts. For the massless neutrinos, they are called ultra-relativistic species. You can have the big omega or small omega of ultra-relativistic species, or the parametrization in terms of an effective neutrino number. So NUR is a contribution of ultra-relativistic species to N effective. And you can mix them. It's your choice. You can say, I will pick up 100 theta S and TCMB and MNU and big omega U. Okay, you can mix as you want. So this comes from a long input module, which has this layer of logic. Okay, next, if you don't want to confuse your user, you should make an effort to be consistent with units. So the convention in class is that by using natural units and proper conventions, you always try to express everything in megaparsecs. And there is just an exception. It's a thermodynamics module, because in the thermodynamics module, we took quantities from other codes, like RegFast. And these other codes had their own choice of units. We did not modify it. But apart from this, everything is written by us and with convention of megaparsec to some power. So for instance, you can realize very quickly that the conformal time tau can be expressed in megaparsec, because the conformal time is like a comoving distance. So it's megaparsec. And the Hubble rate, which in conformal time reads like A prime over A square, is 1 over a time, of course. So it's inverse megaparsec. And then what about densities? Physical density is, of course, in units of, say, grams per centimeter cube. But suppose that I take my physical density and I rescale it by 8 pi j over 3. Then this combination is a contribution to h squared through the Friedmann equation. And the Friedmann equation will use h in megaparsec minus 1. So this combination will be megaparsec minus 2. So every time you will find a background density in class, it will stand for this particular combination, and it will be in units of megaparsec to the minus 2. And then with these conventions, the Friedmann equation is just h squared equals the sum of these densities. The wave number is, of course, inverse megaparsecs. Of course, when you do a plot at the end, very often you want h by megaparsecs. Then it's your task to redefine it. And pk would be in megaparsec to the 3 unless you manipulate the output to get this divided by small h to the 3. Okay, so it means that in the code you don't find everywhere the units written because it is assumed that it is megaparsec to some exponent. Okay, so to get a code which is accessible and self-contained, we choose to use plain C, but with a style mimicking C++. I will explain why concretely. And you could say, but why do you use plain C mimicking C++ and not directly C++? Yeah, maybe it would have been a good choice to use C++. I have no strong opinion on this. Maybe we will do it at some point. Our intention was to keep as many users as possible, and C is still a bit easier to understand for a young student than C++. Okay, but there is no stronger reason than this. And personally, I am always upset when I need to install codes and it fails because the libraries are not probably downloaded and interfaced. So there is 0 library that you need to install together with class, which means that all the numerical methods are coded inside the code. So there is no LAPACK, there is nothing like this. You just install it, and if it's compiled, it works. Of course, the exception is that if you want to use class with a Python wrapper, then unavoidably you will need to download some Python modules. Yeah, so this I admit you need to download NumPy and SciPy, and that should be it. But this is the case for now most modern codes with in Python or with a Python wrapper. Okay, and so to make it accessible, as I said, we have put lots of comments in the code, and these comments look a bit strange when you open the file. There are some funny hashes and signs, because they are supposed to be slightly interpreted by Deoxygen, which is a software to generate automatic documentation. So when we do a new release of the code, we run Deoxygen, it extracts the comments and put them in a nice form, and this becomes the online documentation that I will show later. Okay, what else should you do if you want to be user-friendly? You should be structured. So you will see that class is a very clear succession of 10 modules. Each module has its own task, and there are, as far as possible, no duplicate tasks across the modules. Each module is called only once in a sequential order. So this is in order to achieve this flexibility and modularity of the code. Okay, next objective. We really want developers not to be shy to add a lot of physics in the code. The drawback to this would be that if you add to the public distribution all the models that everybody have invented, the code could become first unreadable and second very slow. So indeed, we don't put all the new models in our public release. We try to select the ones which are of interest for a wide category of people. But still, we tend to accumulate new physics because we believe that we have a structure that allows for it without making the code unreadable or slow. And this is very simple. This could be understood by a high school coder. It's simply that when each time we add a feature, so feature here could be a species in your model, or a physical approximation to the equations, or a new type of observable. It could be lots of things. When you add a feature, you find a nice name for it. Here it's just feature. And everything related to this feature will be in an if loop. Okay, so it's completely trivial, but not all codes do that, actually, surprisingly. So the advantage is that if you want to know every part in the code related to this feature, you search for the flag as feature, and you see everything. But if you read the code and you want to go to the essential, every time you see an if of something you are not interested in, your mind will very easily skip this part. And finally, when you execute the code and the feature is not turned on, because for instance, in the input parameters, say the omega related to the species was set to 0. Or maybe this is a new observable, but in the input you did not require for this observable. Then has feature is false, and the fact that you added this feature will just slow down the code by maybe 10 evaluation of if true equal false. So it's completely negligible. So this is why we are adding and adding new physics without making the code heavier in terms of performance. And something which is slightly always for everybody more difficult to explain is, of course, you should avoid to do hard coding. Hard coding is typically what makes a code unfriendly and unflexible. So we have this very present in mind and at many levels. So no hard coding, for instance, means that you will never find in class, normally, I hope so, if not, you should complain. I will not reimburse you because the code is free, but if you find exceptions, tell me. You will never find a list of hard-coded indices. For instance, if there should be an array of perturbations, you will never find that photons should have index 2 and the neutrinos should have index 6. All the indices are just symbolic and are assigned dynamically by the code, and you never need to know to which values they have been assigned. For you, the index is an integer variable with an explicit name, and the task of associating these variables to numbers is done internally by the code, and you don't need to know. Okay, so this is a dynamic allocation of indices. There is also dynamic allocation of arrays. I don't think there are many places where you will find an array declared with a size of 50, because it's always a code that will see, according to the needs of the run, what are the number of components in this array, then it's allocated dynamically with just a minimal size and freed at the end. All these are canonical rules for coding, of course, but we really took them very seriously. I don't think you will find any number in the code, excepted when there is an obvious factor in an equation. I mean, in the perturbation equation, sometimes you know that there must be a 2 or a 3. Then you will find 2 or 3 written in class. But otherwise, you will find no number, because when you have precision parameters or number of values in which you should discretize or sample a quantity, all these things are written symbolically, and the values are determined for the need of the run. Okay, so there is not a number anywhere saying that you should sample your wave number space over 100 values. The number of values will always be determined depending on what is the output that you wanted. And in the code, you will never find the number, you will always find the integer variable. It means in particular that all the precision parameters can be grouped in the same place. And that's very important, because when you want to tune a code to high precision, if you know that here and there in the code, there is a 200, there is a 500, and there are different numbers governing the precision, and you want to check what is a limit, a high precision limit of the code, it's a mess. You have to search manually for all these numbers and increase them. Instead, if all the precision parameters are variables grouped in one place, you look at an array, and in this array you change your values, and you know that you are continuously increasing the precision of all the parts of the code. So this is also important. You never find global variables in class. Global variables are a nightmare when you try to do parallelization. So the variables are always defined inside functions or as an argument of functions. You will never find a single variable defined outside of a function. That would be a global variable. This I already said. When you need to do some sampling, it will never be predefined. It will be inferred by the code for each model. So for instance, when you integrate perturbations over time, in lambda CDM, you might know that you need a better sampling around the time of recombination. But now if you implement a new dark energy model, and in this new dark energy model, there is a transition taking place, say, at a redshift of 10. If you have hard-coded your precision and your sampling, maybe the code will rush through this redshift of 10, and you will get an inaccurate result. Instead, class will always determine these steps from the behavior of the equations. So in this example, it will detect, when approaching a redshift of 10, it will detect that some quantities are varying quicker, and it will reduce the step size. This is another aspect of avoiding hard coding. And also in a code like this, when you integrate your system of equations, there are different regimes with different physical approximation, tight coupling, radiation streaming, etc. And the time for switching the approximation should not be hard-coded, because if you hard-code it, then you will have an optimal choice for your default lambda CDM cosmology, which could become very suboptimal for another model. So the time for switching the approximation on and off should be always decided by the code, depending on the criterion that you implemented. For instance, switch off tight coupling when the interaction rate is smaller than the Hubble rate, something like this. Okay, so this is a summary of what no hard coding means in class. Another important aspect is error management. Of course, these codes do produce errors when you develop them, and you want to know where the error was. So in Python, it's great when there is an error in your script. The error message tells you in which line is the error. So we have the same feature in class, and to achieve it, we have to obey to a syntax that I will explain tomorrow. The syntax is a bit heavy, but it's very logical. So it's a bit of an effort to learn it, but once you learn it, the benefit is huge, because each time, if you did everything according to these rules, each time that you have an error, you will have a report with a full tree of errors. So for instance, this error occurred in line 10 of this function when it was called in line blah blah of this function when it was called up to the top. And all this is generated automatically by some macros if you apply our coding style. Okay, another thing, so a painful thing for users when they trust a public code is that the versions of the public code evolve with time. And this is painful because maybe you develop some new feature for a version N, and when the version N+2 is out, and you want to use a new thing in N+2, you have to struggle to make it compatible with your version. So to avoid this, first, we keep in mind when we develop, we keep in mind that we should add feature, but not remove or rename all features. And unless it's really unavoidable. So we try very hard to do this. Sometimes when we make a development, we don't take the easiest choice because we know that the easiest choice would break compatibility with old version. So we take a slightly more difficult decision in order not to break this compatibility. We really try to do this as much as we can. Then if you look at the main page of the code, which is here, or on the GitHub repository of the code, you see a clear history of what has changed in any version. So you can track back the feature in which you are interested. And of course, we completely develop with the logic of Git. I guess that most of you know Git. So because we develop on Git and try not to break old things, in principle, a Git merge would solve your problem of importing your developed feature in a newer version. Sometimes there will be a conflict to fix, but I would say most probably rarely. Okay, yes. So these were all generalities. Now you want to check concretely if it works, if I'm not lying to you, by looking at a bit more at the details of the code. So we will start with the first step, which are installation and basic usage. So for installation, we sent some explanation, and since I'm at right in time, approaching to the end of this first lecture, let me tell you quickly what you have to do. So you can choose to download the .tar.gz. This is old school, and then you uncompress it and you learn how to use it. And then if you do your modifications, and you want your modifications later on to be propagated in the versions of your friends or in a newer class version, you are stuck. So the modern way to get the code is not to download the .tar.gz or .zip, but to do a Git clone. Then you get the full repository, and if you know the logic of Git, you will do your developments with lots of commits, with visibility on your previous commits, possibilities to merge with other versions. So I'm not here to advertise Git. I think most of you must be using it already. And if you are beginning in the field and you have not learned Git, really, I should say it's worth spending 3 days learning Git well, because it's extremely useful. Okay, so suppose that you have downloaded or cloned the code. In principle, you just need to compile with a make clean and make. The -J is for faster compilation on multi-threads. And then we will see that this is a reference input file. If you can run this command and you get some output, everything works nicely. Now, what is usually easy in Linux and more tricky on a Mac is the compatibility between the C code and the Python wrapper, because you have to think of installing Python modules that are compiled with the right C compiler. So if everything works nicely, when you do a make instead of just make class, it will first compile the C code, and usually there are no problems. And then it will compile the Python wrapper, and this is where you might see a problem of compatibility. If not, you have the impression that there were only a few warnings and no errors. You want to check that the Python wrapper is installed. You open a Python window, and then class should have already been installed by the make command, should have been installed on your computer as a Python module. You don't need to, it's not another step you need to do yourself. And to check that it has been properly installed, so the new Python module is called classy. And if you say, for instance, from classy import class, there is no complaint, really everything works well. And if you run into trouble, especially on Mac, you can have a look at this address to try to solve your problem. Okay, I think this is the last slide of this basic lecture. So we have time for a few questions, then we will break. And after the break, we will start with the class usage. Questions? Yes.
Go over this later, but can you use your seat mic, please?
Yes. I should announce this. So if it's nicer if your questions are recorded. And for this, you need to press the mic button, the black button here. And then, okay, your question will be recorded. Very good.
Yeah, so you might go over this later, but in terms of doing the Monte Carlo, what's the best way to interact with the class?
Yes, so I will mention a few possibilities in the last lecture, but I can anticipate that many of these Monte Carlo samplers are interfaced with class. Initially, we developed our own sampler, MontePython, and it's still maintained. And actually, the one, so it started to be developed by a former PhD student. And now the most active person in maintaining it is a PhD student who finished last year, who is now in Stony Brook, and he will join us, I think, at some point later in the day, Thijs Brinkman. He's still actively maintaining it, answering to the forum, so you can use MontePython. Personally, I'm very happy with MontePython. Then Joe Zuns, the developer of Cosmosis, added the compatibility with both COM and class. So when you use Cosmosis, you can choose which code you want. And sometimes it can be a very good idea to do a run with each to convince yourself that there is no systematic coming from the Boltzmann code. For instance, if you want to do run at very high precision because you are doing forecast for a very precise experiment like PICO, it can be a nice experiment to check that the two codes give you the same posteriors. And now in Aachen, we have a very skilled cosmologist and developer, Jesus Torrado. So he has written a very nice sampler called Cobaya. He developed it mainly when he was in Sussex with Anthony Lewis, but in close contact with me also. And they have released this code, and this code is completely democratic between class and com. It uses both indifferently. So you have the choice between at least 3 public Monte Carlo sampler that are interfaced with class. Cobaya is the one with the most modern style. It's very nice. I recommend trying. Yeah. Okay. Fantastic. Don't hesitate to ask questions also during the break. And when the lectures will become more concrete, I hope very much that you will have more questions. Thank you.